Hi everyone. Today we're going to be looking at the first section of Chapter 5, which is about discrete probability distributions. It's section 5.1, and it's about the basics of probability distributions. So if you go back to the first chapter, we talked about different types of data that resulted from collecting information, variables. They were qualitative and quantitative. So no matter what type of data that we collected overall, we always need to be able to convert that data into numerical quantities in order to analyze it. Okay, so we create this thing called a random variable. In this chapter, most of the time we're going to be taking qualitative information and converting measurements of qualitative amounts, as in percentages and counts, in order to analyze them using statistics. A random variable is this part right here. And a random variable is a numerical count or measure of an outcome for a probability experiment. So its value is determined by chance. So we don't know, for example, when you roll a die, what's going to happen. Will it be a 6 or a 2 or a 3, 4, whatever. So random variables are usually denoted by capital letters such as x, although we also use lowercase x quite a bit as well. We usually use the abbreviation RV to stand for random variable. Okay, so as we saw back in Chapter 1, just like with data, we can have discrete random variables, and discrete random variables arise from things that we would count, such as counting the number of children in your home or the number of cell phones you've owned over the years. Continuous random variables are things that you measure, like the height of a person or the weight of a person or the length of time it takes a drug to take effect, become useful to a person in a medical setting. So basically they're the same things we saw before, except a discrete variable is one that we count and a continuous one is one that we would measure. So just keep that in mind. So examples of each one that are given here. If you want to talk about how tall is a plant, if you give it some new fertilizer, if you're measuring that, well, it's a measure, so it would be continuous. Continuous because you're measuring the height of the plant. If you count how many fleas are on a prairie dog, that would be discrete because you're counting the number of fleas, right? Okay, so if you take all the possible probabilities that you put together, basically like a relative frequency distribution that we saw in Chapter 2, then you have what's known as a probability distribution. And in particular, we're dealing with discrete probability distributions. So what is it? Well, it's a table. It could be written in a graph, or it could be written in a formula, as we'll see in the next section, that gives every single possible value for the discrete random variable, along with the corresponding probabilities. So there's two things we have to check. Some of the homework problems you will see will ask you, hey, is this a probability distribution? And you got to check two things. First of all, that everything that they claim as a probability has to be between 0 and 1. If it's not between 0 and 1, then it can't be a probability, so it couldn't be a probability distribution. The other thing that we sometimes will forget is that the sum of all the probabilities have to add up to 1, or 100% if they're written in decimal form. Okay, so those are the two things you got to check. So in this case, this is our first example. It's a probability distribution for the size of a household in the United States according to the 2010 census. Now what it gives you is the size of the household is 1, so there would be one person in a household, and that was 26.7% of the country. 2 people living together, 33.6%, 3 people living together, 15.8%, etc. 7 or more, we'll end up just calling that 7 for the purpose of doing our calculations. Okay, so that's what this distribution tells us. If you add up all those percentages, you should get 100% or equal to 1. Okay, so what can we do with this? Well, one thing we can do is we can make a histogram out of it. Another thing we can do is we can just look at what the probabilities mean. Okay, so looking at part 2, interpreting and graphing a probability distribution, we're going to use the same data, and now I want to find and interpret the probability that a household has a size of 3 people. Okay, so that's the part that's highlighted right here that's kind of red. If you want to find the probability that a household in the US in 2010 had 3 people living in it, then that's 15.8%, and it just gives you that directly out of the table. And we'll get more into that at the end of the section as we go through this chapter. Okay. The second thing we can do with this is we can draw the probability distribution in the form of a histogram, like this. So we look at that and we think, wow, that looks like a histogram like we did back in chapter 2. And it does, except it's for discrete data. 1 through 7 is what's listed there. But we could also describe it. We can start to describe it in ways that we've described distributions before. And of course, they weren't probability, they were just data distributions. In this case, we can see this guy is pretty skewed to the right. So we would say things like, well, we would expect the mean would be pulled to the right because, of course, the mean chases the tail. The median would be somewhere closer in the middle. But when we're dealing with a probability distribution, it's hard to say what a median actually, what it is. It's not the middle value in the data, it's something else. Okay, so when we have these things, we can start to look at calculating the mean and also how widely spread it is. The dispersion is the standard deviation. Okay, brings us to this. Calculating the mean and the standard deviation. There's 2 formulas. The mean, also known as the expected value, is this symbol right here, the mu with a little subscript x, and it's the sum of the x's times the p of x's. And I'll show you how to do that in a moment. The standard deviation is the sigma with the subscript x, and it's this formula right here. This is actually a computational formula. It's written other ways as well, but that's the one that's easiest to use, the way I'm going to show you how to do it. Okay, you can get this using StatCrunch, and I will show you that as well. First, let's do it by hand. So, same data. Household size for the US Census from 2010. These are the same numbers we saw before, except I'm going to write them vertically. So here's x is the size of the household, and here's the probability. And I'm going to replace 7 or more with just the number 7. So what we do is we need to get the sum of the x times p of x's. So I make this green column right here, and I multiply each x value times its probability, and write it right there in green. 2 times 0.336, for example, is 0.672. And then I total these all up and I get 2.525. And that's the mean. So if we look at that happening right here, if you just add them all up, it's actually 2.525 right there in green. In order to get the standard deviation, we need to take the sum of the x squared times p of x's. You look down here at the formula, you've got the sum of the x squared times p of x's minus the mean squared. And we're going to plug those into this square root formula. So we'll have the square root of 8.399 minus 2.525 quantity squared. I yellowed that, so we square that. We can see that's what you get. Then you do the subtraction by order of operations. And the square root of 2 is about 1.422. Now we're getting those numbers I'm plugging into that formula. Again, here's the x squared. This 1 is 1 squared. The 4 is 2 squared. The 9 is 3 squared. The 16 is 4 squared, etc. And then I multiplied each of the x squareds times the original p of x. And that became this blue column right here, which I summed up. And that was 8.399. And that is what I plugged in right here for this whole blue thing, 8.399. And then went on with the order of operations. So to note that correctly, we would say the mean is 2.525 people, or basically 2.5 people living in a household in the US in 2010. And the standard deviation is around 1.4 people. Okay, so that tells us what we expect. Now, the alternate solution was B, to use StatCrunch. And to use StatCrunch, and you look in the book, it has the order you go through. You go to Calculators, and then Custom, and then a pop-up window comes up, and you choose the values in the household, and then the weights are the probability for each size. And then you click Compute, and this is what you get. Okay, well, let's look at that actually in StatCrunch and watch it go through all the way. Okay, so here we are in StatCrunch. Here's the data. X is the size of the household, and these are the probabilities right next to them. So we go to Stat, Calculators, and Custom, because this is not a normal distribution. It's not something we have seen before. And then we select the size of the household is X, and the weights are the probabilities. And click Compute. And there you go. So this tells us, and wow, look at that, it tells us the mean is 2.525, exactly what we got before, and the standard deviation is 1.422. It has the added benefit that if we want, we can find all kinds of probabilities. For example, the probability that x is less than or equal to 2 is 0.603. I could change this less than or equal to greater than or equal to 2, and now that's 0.733. Or I can make this 4 or 5 or something and get some different probabilities. It's kind of nice because it highlights the one that you're counting as red. Okay. That ends this portion of the video. We will come back and we'll do the next portion in a few moments. Thanks. Bye.